according to this computer. Okay, Chepo, you have to turn on your camera and microphone. Okay, today we're going to continue our lecture on lecture number 3, decision trees. Okay, last time there were some things that I didn't quite satisfactorily answer, even from my point of view. I think I didn't explain it very well. So I have to go back to them so that because my feeling was that I didn't, even myself was not satisfied with my answers. So for you, for sure, you were not also satisfied. So now let's start with that one. I'll share my screen. Shift F5. I'm recording. I'm sharing. I'm not sharing my screen. Yeah. I have to share first, right? I didn't share my screen. So share screen. This one, share. Okay, now it is shared. Now I'm going to, okay. So the first thing that I didn't, took note about the topic that I didn't quite satisfactorily discuss, what was that about the NP completeness of decision trees problem. So what is NP complete? NP complete, the non-deterministic polynomial time complete. That is the exact meaning of NP complete problems. Non-deterministic polynomial time complete. So what does it mean? So the meaning of it is that each solution can be guessed and you can verify it in a polynomial time. That means there's a solution that you can find. Okay? In a given time, you will find it, definitely. Okay, it's not a problem that there's no solution. There is a solution, and given a particular time, given a time for you to work on the solution, you will find it. It can be even solved by brute force. You know, brute force, that means searching, searching all the possible solutions one by one. It's like, have you tried to open the bicycle keychain with numbers alone? I mean, with the lock that is the numbers combination. Okay. So, and you forgot about the numbers. So all you need to do is go through each combination of numbers, then you will be able to unlock your bicycle. Okay, the same thing. That's called brute force. There's no specific solution on what exactly is the path to take, but just try out all the possible solutions to find, in order to get the solution. Okay, so you try out all the possible combinations to unlock the bicycle. That's brute force. Okay, so in some cases we go through. So that means that NP complete. The problem of decision trees is NP complete. That means you can find a solution to the problem given a particular time. Given certain time, you will always find a solution. Okay, you can even resort to greedy solutions, and you can also find it. Okay, so that's the description that I want to tell you, the explanation. So for example, here, if you want to search using greedy process on the second bullet, you can say you start with an empty decision trees and then look for the split. That means that which attribute that you want or feature that you want to branch out, and then recurse, that means do again. Okay, and continue until you reach the leaves. Okay, this one, I think we have done that. So now, the other one that I want to say, we already mentioned that the entropy is a measure of a measure of an attribute where you're going to make your decisions in terms of splitting or branching. So entropy, we're saying that it is a measure of uncertainty. The more uncertain the things are, there's more entropy. So in this case here, this is the probability of getting heads or tails. So probability of getting heads, you get a 1 when the result is a head, and you get a 0 when the result is a tail. And halfway through is half of the probability of getting heads or tail, and this is where the most uncertain part is of this whole exercise. So here you are certain that you won't get a head. Here you are certain that you will definitely get ahead. But in the middle, you won't know whether you will get ahead or the tail, because there's equal most in the region, almost an equal chance of getting heads or tails. Okay, so this is where you are very much uncertain, and so this is where we are more interested in, because the approach here that we are going to do is we select the most uncertain attribute first in order to narrow down to the problem. So once you take the one that's most uncertain, and then you go slowly and go to the next level until your certainty becomes more pronounced. Okay. So that is the measure of entropy. And so we have, we saw this one, this one. I want to, this is the entropy equation that we are looking at, and it is a function of log 2. Okay, this is an important information that I want you to look at. So now, okay, the first term is a probability. So this probability, 5/6, the yes or the true. 1, 2, 3, 4, 5, 6. So there are 5 truths and 1 false. And there are 6 outputs. So 5/6 is true, log 2 of the same probability, 5/6. So now, this log 2, how does it look like? So log 2, I plotted this one. I mean, just show this to give us some overview. I mean, a reminder of what log 2 plot is. And so in this case, our probability always goes from 0 to 1. You agree? Yeah? Always between 0 and 1, our probability. So that means that these terms here, because these are all probabilities, this term is always between 0 and 1. This is always 0 and 1. Okay? So in terms of the log 2 graph, which is this one, we're always looking at this region here. Okay. See, now I can hear that you're watching movies. So here we are always looking at this region. Okay, between 0 and 1. So that means the log 2 values can be negative number from big negative number up to 0. Okay, so that's log 2. This part here is from negative infinity to 0. Okay, so that means at some point it becomes negative infinity if your probability is, the probability is very, very small. If the probability is 0, okay, this is one most important thing that I want you to remember. If this is 0, log 2 of 0 becomes negative infinity. Okay, it is not a number. So what happens if log 2 is 0 here? So we just disregard this. Okay, but here if this is log 2 of 0, that means 0 multiplied by log 2 of 0, that means 0 multiplied by infinity, by negative infinity. Well, for practicality's sake, any number multiplied by 0 becomes 0. Okay, we can assume this to be 0, but mathematically, strictly speaking, it is not a number, because a number multiplied, this is infinity. Okay, you are dealing with infinity, and multiplication only deals with real numbers. Okay, anyway, an infinity is not a real number. So now, so if these things become 0, or the probability here is 0, so 0 times log 2 of 0, which is infinity, so we assume this to be 0, and then we will concentrate on the other parts. Okay, that's the other one that I want you to take note. Okay, let's clear this one. Okay, let's continue. So here, this another thing that I want you to look at. We are looking at conditional probability. So given y the output and xa, this is what I missed to that's why it became very confusing last time. So it is the y the output against the parameter or the attribute xa. So there are many attributes. In this case here, the attribute, call it attribute here. In this case, there are 2 attributes. x1, and x2. Okay, but there's only one output, y. Okay, please take note of that. And so these conditional probabilities apply, this conditional probability applies to the output with respect to a single attribute. Okay, that was what missing in our discussion before, because I assume that the attribute here, it goes through all the attributes, but no, it is only for one attribute. Okay, so that means in this case here, this equation, let me erase this. Okay, now let's deal with this equation. So in this equation, it goes through all the attributes of XA. In this case, for example, if we use the attribute X2, so all the attributes of XA, in this case, it becomes true or false. So this is true or false. Okay, there are two probabilities, and then this one, that means J1 to V is equal to 2. Okay, so this one, it can be true. We look at the true part, and then in the second round, when K, that is K is equal to 1, and then in the second round, K goes from K. In this case, K, be careful here. Okay, when this is true, then you, when we choose to be true here, then we do true here and true there. Okay, that's when J is equal to 1, and then here K is equal to 1, I is equal to 1 to K. So I applies to the output. In this case, true or false also. K goes from 1 to 2. So you have true and false. So this is also 2. This is also true, and that's false. Sorry, this goes to true when XA is true and when XA is true. Okay, and then in addition, maybe let me just write it down so that it will be much clearer for you rather than talking. Okay, I want to expand this one so that we can have a better. Sorry, let me. No. Okay, text editor. Okay, there. Let's do the text editor, and then let me go here so that we can look at it properly. Okay. I guess you can see this, and then let me do the annotation. Clear all. Okay. Now, draw. Can you see it? Is it clear to you? This one is clear?
Yeah, it's fine.
It's fine. Okay, now, so let's do X. I mean H, entropy, conditional entropy of Y with respect to one attribute XA. Okay, so in this attribute XA, I'm just rewriting this. Okay, so that we can use one attribute. So we assign XA to be, let's just say X2. Okay, so where is X2? X2 is this one. Okay, and your Y is this one. Okay, so that means that we will consider only this table now. Okay, so let's write it down. So now we say that H, we spell out all the indices so that it will be clear to you of XA. In this case, this is X2. Okay, the conditional entropy of the y output given x2, which is x2 is one of the attributes. So now we say it starts with minus probability of x2, okay, x2 being true. Okay, this is the first one, multiplied by probability of y equal to true. Okay, remember here there are two probabilities of y, 1 to 2. Okay, let's start with y being true, and then given, in this case you have x2, given x2 equals true. And then log 2 of the same thing, probability of y being true given x2 equals true. Okay, but then that is the y being true. Now we consider now this I goes from 1 to 2. Now the next summation is for probability of y being false. Probability of y equals f given x2. Again, this is, we are considering x2 to be true. So x2 is true here. Only the y changes. So log 2, probability of y now being false given x2 equals true. Okay, that's the first term when j is equal to 1. When that means x2, when x2 is equal to true. Now the second of this summation becomes minus p when x2 is false. Okay, multiplied by the summation inside summation. Okay, so we just repeat this part. We repeat this part where your x2 now is true. Okay, so let me write it down. Undo. So p y equals true. Okay, given now x2 equals false. Okay, it's quite difficult. I have to make your f nice so that it will look different. So log 2 of p, probability of y equals true, because we go through the y being true and false. So x2 here in this case is false, because this is the case of the false x2. Okay, plus the next one, p, where your y becomes false, is you go through true and false of y given x2. X2 in this case is always false. Log 2 p of y equals true. No, sorry. Y equals false, because we go through y equals true or false, given x2, this is the case of x2 being false. And then close. That's it. Okay. These are all the conditions. This place here is all the conditional probability of the y output given the x2 attribute. Okay. So how do we know this? So now we say that when, okay, let's fill up the numbers here. Okay, so now let's say green, blue. Okay, what is x2 being true? Probability of x2 being true. This is about x2. Yeah, so it is about x2 being true. So how many are there in x2? How many elements? 1, 2, 3, 4, 5, 6. 6 elements. How many are true? 1, 2, 3. So that's 3 over 6. This is 1/2. Okay. Now, probability of 1, 2, 3 over 6. Did they? Okay. This is x1. Or maybe we should do x1. You want x1 so that we can verify here? Okay, let's do x1. Let's do x1 so we can verify the numbers here that this is correct. It will help us to convince ourselves that we are correct. So let's change this one to x1. x1. Okay. There. And this one. Where else? This one. So x, this one. Okay. So now we say x1. x1. So x1, and then x1, 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 x1. This is x1. So x1, 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 x1. Okay. So now, so let's do this. Let's take the blue. So probability of y given x1. Okay, probability of y. So now this is this x1 and this is y. So now y x1 alone, probability of xy being x1 being true. So 1, 2, 3, 4. So that's 4 over 6. So this is 4 over 6. Okay. Probability of x1 being false. So there are 6 entries, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And there are 2 entries that are false. So that's 2 over 6. So this is 2 over 6. Okay. Now, probability of y being true given x1 is true. So when is x1 true? So we look at the part where x1, this is the part when x1 is true. So x1 is true is this part. Okay. So now we only consider this part here where x1 is true. Okay. So x1 is true. What is y? Y is true given x1 is true. So we only this table where x1 is true. So y is true, so that is 4 over 4. So this is 4 over 4 or 1. 4 over 4. Okay. X1 being true and y is false. That's 0. There's nothing. That's 0 over 4. And this is 0 over 4. There's no false. Okay. Next, this is x1 is false. So x1 is false is here, the second part of the table. And then y is true. So true, that's 1. That's 1 over 2. Y is true when x1 is false. So that's 1/2. Okay, this way is 1/2 also. Y is false given x1 is false. So this is also 1/2. Okay, 1/2. Okay, then we check. Okay, against here. So now you have 4 over, oh, how come? Yeah, this is 4 over 6. Let's mark. Okay, this is 4 over 6. That's correct. This is 2 over 6. That's correct. Okay, log 1. 1 log 2 1. So this is 1 and that's 1 and this is 1. That's correct. That is this part. And this is 0 log of 2 0. That's correct. That's that part. The second part is 1/2 log 2 1/2. That's correct. This is the first part. And then the second part log 1/2 log to 1/2, like that. Okay? Any questions? So that's how you get the conditional entropy of one attribute. So now this is for x1. For x2, we are going to repeat the whole process, but now instead of x1, then this one becomes x2, like that. Okay? This one becomes x2. Okay, let's consider what will happen if this is x2. Or maybe let's just undo everything. Now let's consider x2. What will be the values of x2? There. Okay? So now let's do x2. So if this is x2 now, so x2 being true. So 1, 2, 3. So this is 3/6 or 1/2. And this is also false. 1, 2, 3. So that's also 3/6 false. Okay? So when x2 is true, this one, and that one. Okay? So when x2 is true, the y is also true. So this is 1. This is 3/3. That's 3/3. And this is 0/3 because there's no false. The output is never false when x2 is true. So 0/3. Okay? So now when x2 is false. So when x2 is false, we look at this one, x2 is false, x2 is false. Okay, when is y true? So 2/3. Y is true at 2/3 and then 2/3. Okay, and the same thing when is it false? Is 1/3. So 2 times that becomes true and 1 time becomes false. So 1/3 and 1/3. Any questions? That's all. So here this is 0. We don't take this one, becomes 0 because this is 0 and now this is 1. Log 1 of log 1. Okay, and then log 1. What is log 1? We have seen that already. It's here. Log 2 of 1. Log 2 of 1 is 0. Input is 1, that's 0. Okay, this is also 0. Anyway, you will find it in your calculation later. But any questions on this? We're just applying the formula. So you can apply it for each attribute. Okay, so now let's continue. No questions? So let's move on to the next. Tell me we'll have a break at 12 o'clock. So now we have done this equation of log 1. Okay, this is the x1 attribute, and we compute that. And so here now you have your information gain is your absolute entropy minus the conditional entropy for x1, for example. And so what we are saying here is that we will take the highest information gain. Please listen. We will go through all these attributes, okay, the information gain for all attributes, and see which one has the highest information gain. The highest information gain is defined as the absolute entropy of the output minus the entropy of the output given one attribute. Okay, so we have to go through all the attributes. How come it's very noisy? Who is that? Somebody is doing an electric fan. Who is that? Camela. Camilla,
Yes.
you have like this background
Yes.
sound. You have a background sound. Is there a wind there?
Oh, I'm in the no, I'm in the lab.
Is there a wind like blowing? Okay, can you just mute
No.
the microphone? Can you please mute it and see if it's you?
Okay.
Yeah, it's you. So keep it that way. Sepang, Sepang, you turn on your microphone and your camera. Okay, let's continue. So now, please note that we are going to choose the highest information gain. The one with the highest information gain is where we choose the node, where we choose the next split. That's what we say, next split. That means the node of the decision tree. For example, here. So we are, for example, we don't know which node we should be the first in the tree. So whether A, B, or C. So now we have to go through all the attributes in order to find the highest information gain. So the equation of the information gain is this. So you have to go through for each attribute. So that means that in the case of this one, we are saying that in the case of x1 or x2, so we have already computed for x1. So we say that information gain, okay, for given x1 will be the entropy equal to the entropy of the output y minus the conditional entropy of the output y given the attribute x1. Okay, so this part here we have already computed from the previous slide. Okay, so let's go back to the previous slide. Yeah, so here this is 2/6. So we write it down. This is already 2/6. Okay, as computed from here. Okay, now what is h of y? Okay, so let's go back to the absolute entropy equation. So the absolute entropy equation, this is, we have computed this one. We go through all the possibilities of in case you forgot, let's just write it down. Okay, all the possibilities of the output. Okay, so that one. So hy is the negative of the probability of y being true. Okay, log 2 of y, probability of y being true. Then that summation is representing all the possibilities of y. In this case, true or false. So up to 2. So minus the probability of y being false. Log 2 of the probability of y being false. Okay. So we count y being true. So what? There are 6. 1, 2, 3, 4, 5, 6. So true is 5/6. So that is 5/6. And log 2 of 5/6. And then the false is 1 divided by 6. And this is 1 divided by 6. So all these are computed. So this is 5/6, log 2 5/6 minus 1/6, log 2 1/6. So that's 0.65. So here, so now this is 0.65 minus 2/6 or 1/3. So that means that one is equal to 0.65 minus, what is 1/3? 0.33. Thank you. Okay. So let's check. So now the information gain is 0.65 minus 33. So what is this? What is that value? How much is that? It's greater than 1, we know, but 5 minus 3 is what? 2. 6 minus 3, that's so 0.32. Okay, so if we do it, okay, let's calculate for information gain for x2. How do we do this? So now the same thing, the absolute entropy of the y output, the same value will be 0.65. Yeah, here it will become 0.65. Okay, minus I want it to be minus h of the output y given x2 attribute. Okay, so we have computed this before, so let's go back to here. Let's copy what the x1 has here. So let's copy this one. So okay, we know that this is the probability of the y being true. So y being true given x1 to be true. So x1 to be true. Now we want the x2 to be true. So let's what did we say here? So x2 being true is this one, and this one, and this one. Okay, so the first one is the xa, x2 being true. So x2 being true, 1, 2, 3. So that is 3/6. So this is 1/3. This part is 1/3. And this is also 1/3. Any questions for this one? 1/3 and 1/3. Because now we are considering x2, okay? So x2 being true, this is this part here, the absolute probability. So x2 being true is 1/3 out of 6, and x2 being false is 1/3 also out of 6. This one, 1, 2, 3. Okay, so now the next one is when is y true when x2 is true. So when x2 is true, y is also true. So this is correct. It applies. This is 3/3 log of 3/3. That means 1 log of 1 plus when is y becomes false. Y becomes false when x2 is true. So nothing. It's 0/3. So 0/3. So this is 0. That's 0. And the thing is, this one is also 0 because log 1 is 0. Okay. Now let's consider when x2 is false. Any questions? Please ask me. Is this clear? So now let's consider y being true. So y is true for x2 false. So true. This is true. No. See, yes, that's true. And yes,
the first probability. The first probability, is it 1/3 or how?
Sorry.
The first probability of x2 being true, where you have written 1/3, is it not 1/2?
This one.
Yes, sir.
Let me check. So we are saying probability of the x2. This is that part. Okay, let's remove the arrow. Sorry. To make it clear. Okay. Now what we are looking at is this term. this term, okay? Probability where our XA is X2, okay? Correct? So this is X2. So this is X2. We are looking at X2 true, okay? Probability of X2 being true and another probability of X2 being false, okay? So what is the probability of X2 being true? So that is absolute probability. So we count the number of true X2. 1, 2, 3. Okay. There are 3 truths and then how many elements? 6. So that means 3 over, that's right. It's 1/2. So let me write down 3 over 6, right? So that is 1/2. It was supposed to be 3 over 6. Thank you. And then this is 1/2, and that is also equal to 3 over 6. Okay. Yeah, thank you. So you understood. Okay. So that's 3 over 6. This is correct now, and this is correct now. That okay? And then now when you have y being true given x1 being x2 being true, so this one x2 is true, these red boxes here, okay, and then how many, given all these red boxes, how many y's that are true? So 3. So 3 over 3. So this is 1 log 1 and nothing about false. So 0 over 3. 0 log 2, 0. So this is correct. Now let's consider the case when x2 is false. So x2 is false. Let's mark it separately. Green. So x2 is false. This one, 1, 2, and 3. And how many are true? So 1 and 2. So now this is 2 over 3. So this is 2/3. And that's also 2/3. Next, this is 1/3. And this is also 1/3. So now, this part, if we finish this equation, will be minus. So now, let's input this equation here. So all these are 0. So the first term is 0 because this 0 plus 0. So that's nothing. So now this is minus, what was that? This is 1/2, right? Minus 1/2 times, okay, 2/3 log 2 of 2/3 plus 1/3 log 2 1/3. Can somebody calculate, please? How much is this? So 0.65 minus some value. Then we will know which one should be which has the highest information gain, and then we will use that as our first layer. Which one? Or you want me? Are you calculating? Run it using Octave. Okay. Nobody, I guess, wants to do it. Can somebody do it? Font size, make it 18. Okay, I'll do it here. So 1/0.5 times log 2 0.5, okay, plus, no, this is 2/3. It's not 0.5. 0.5 times 2/3. 2 over 3 times log 2 of 2 over 3. 2 over 3 plus, now you have 1/3 times log 2 of 1/3. Okay, so this is minus 0.46. Okay. So this is minus 0.46, but with the negative sign, minus. Okay, so it becomes minus minus plus. So what is this now? 5 minus 6, that's 9. Okay, correct? And then 5 minus 4, that's 1. Okay, so 0.19. So 0.4, the information gain when you consider the second attribute x2 is 0.19, but when you consider the first attribute x1 is 0.32. So we choose x1 to be our first node where we're going to split. So if we write the output here, it will be x1 first, okay, and then split to x2. Okay, and we decide how x2 is being split, then we can. Okay, then we can find the answer, true or false. Okay, true, false, x2 like that. True, false also. Then we can find what will be the answer here. So when x1 is true and x2 is true, that's true. Is that the one? When x1 is true and it's false. Okay, anyway, we can look at this one. Okay, so understand. So the tree will look like this, similar to that, because we have identified which one is the correct first node, the one with the highest information gain. Okay, we need to have a break first, and then let's see you 10 minutes, so 2:20 or 5 minutes. Oh yeah, just say 2:20. Okay, any questions? Questions? Everybody still awake? Okay, I will see you in 6 minutes. Okay, bye.